Hi guys, Assalamualaikum. Good day everyone. So this is part 2 of the shear wall design to Eurocode. Last video we stopped here at the win action. So what we have done in part 1 is we just figure out what is the action. We have the action on slab, and we also have found what's the action at the bottom of the wall. So from at the action at the bottom of the wall, we have this GK where the total GK is 200.83 kN per meter. The total QK is 59.4 kN per meter, and we also have this wind action that comes from the wind pressure, 1 kN per meter square, and for each wall, it is subjected to 333 kN per meter. So what is the next step? As I mentioned at the end of video for part 1, we are going to look at the in-plane action and the transverse action. So what does it mean by in-plane action and transverse action? So first thing first, let's look at on the in-plane action. Okay, we are still in step number 1 for action. So I'm going to use color blue. Okay. So in plane action, in plane is where it is parallel to wind load. Okay, now what we want to find here actually at the in plane action is we want to figure out what is the maximum and minimum design ultimate vertical and horizontal action. Okay, this word ultimate is where we are going to times with the safety factor of 1.35 and 1.5. This is where this is a step now. And let's look at on the formula of this maximum and minimum design ultimate. Okay, before we go further, let's look at on the formula. So maximum design ultimate vertical action first. Okay, and vertical action due to wind load. Okay, at the end of the wall, not due to the wind load, due to the GK, QK and wind load at the end of wall. And the formula is, this is NED max. Max represent this maximum here. Oops, sorry. Okay, so what are the formula? 1.35 GK, or we use the big GK, right? Let me erase it. Just not to get confused here, we use the GK and QK here. So GK plus 1.5 QK plus WK. Okay, so we have the GK, QK and this QK. The WK here is this is not at the end of the wall. This is the wind pressure, and we divide by the 2 of the wall. Okay, wall 1 and wall 7. To find the WK, okay, we have GK, we have QK. Now what we want to find out here is now WK. How do we find the WK? Let me write down the what is WK here? This is a vertical line. Vertical action at the end of the wall due to wind. Okay, due to the wind, WK. Now, here what we're going to do. This is your building. This is your WK equals to 333 kilonewton per meter. Okay, that we have calculated previously. The height of the building is 17.5 meter, and you have stump of 1 meter. Okay, now to find WK, the vertical action at the end of the wall, the formula here for WK. Okay. Oh, okay. Dia jadi macam tadi. Not sure why. Alright, it's okay. Okay. WK here is equals to M over Z, where Z is equals to BL square over 6. Okay, Z is equals to BL square over 6, and then if we rewrite this formula, not rewrite, rearrange, okay, we will get 6M over BL square. Okay, so we need the B, we need the L, we need the M. So what are the value here? M, we're going to find out M later on. B is the width of the building, and we know that the width of the building is 36, right? 36 meter. But just like as we design a slab, we are going to use per meter width. Okay, so the B will be 1 meter. Okay, we just take per meter width only, and then L is here. Okay, how much is this? Let's look at. So this is the wall 1 or wall 7. Okay, this is wall 1 and this is wall 7. So let's say we are designing the wall 1. It is similar. Okay, we design the wall 1 is the same as we design the wall 7, because it is symmetric, it has the same load, it has the same dimension and all. Okay, so for this wall 1, okay, and the L is 5 times 5 times 5, not times, sorry, plus 5 plus 5 plus 5. Okay, this is the L. This is the B. Just now that I said 36 meter, but we are not going to take B as 36 meter. We are just going apply as a slab. We are going to take per meter width. So times B equals to 1 meter here, and the L here is 5 plus 5 plus 5. You have 15. So this is 50 meter. Okay, so your L is 50 meter, B is 1 meter. Now what is M? Let's look at M. M is bending moment at bottom of wall due to wind action. Okay, and how do we calculate M, bending moment. Okay, bending moment, you have this, okay, at the bottom of the wall, moment, right? Just like moment, we have the load just times with the lever arm. Okay, so what are the total here? This is half. Okay, we assume that the wind action is imposed at the mid height of the building. So this is where 17.5 divided by 2 is 8.75 meters, and you have this stump 1.0 meters. So your lever arm is 8.75 plus 1, so 9.75. Okay, and the load is 333. So 333 times with the lever arm 8.75 plus 1. So that is your bending moment. 333 times the lever arm 8.75 plus 1, you will end up with 3246.75 kilonewton meter. Okay, so once you have M, you have we have figured out what is B, we have figured out what is L, then we can get what is the WK here, the vertical action at the end of the wall. So vertical action at the end of wall due to wind action. Okay, so your WK is equals to M over Z, or 6M over BL square. So 6 times 3246.75 divided by B is 1 meter, L is 15 square. Okay, you will get 86.58 kilonewton per meter. So this is your WK. Once you have the WK, we can plug into the formula of NED max here. Okay, and GK and QK, the value of GK and QK is from here. QK is 59.4, GK is 200.83. So let's plugging into the formula of maximum design ultimate vertical action at the end of the wall, at the end of the wall here. Okay, due to the wind that come from here. Okay, what is the vertical action at the end of the wall? So maximum design ultimate vertical action at the end of wall. Okay, NED max is equals to 1.35 GK plus 1.5 QK plus WK. So 1.35 GK is 200.83 plus 1.5 QK is 59.4 plus WK 86.58. Okay, and you will end up with 490.09 kilonewton per meter. If you get slightly different value, maybe it's because of the decimal point. It's okay, slightly different. 490, just the decimal point slightly different. Okay, now this is the NED max, and we need also the minimum here. Okay, as I mentioned earlier, we want to find what is the maximum and minimum. We have found out what is the maximum action. Now, what is the minimum action? Let's figure it out. The formula for NED min or minimum design ultimate vertical action at the end of wall. Okay, the formula is NED min is equals to 1.0 GK minus 1.5 WK. Okay, so 1.0 GK is 200.83 minus 1.5 WK is 86.58 just now, and equals to 70.96. Okay, kilonewton. Tadi dah letak unit ke belum? Kilonewton per meter. Okay, kilonewton per meter. Okay, we have the NED max, NED min for vertical action. Now for the horizontal action. Okay, for horizontal action is where we are going to use it for shear design later. Okay, so for maximum design ultimate horizontal shear, okay, VED, horizontal will refer to VED for the shear wall. So VED is equals to 1.5 WK. 1.5, our WK just now is not the WK that is 86.58, but the WK here is the 333 kilonewton per meter. Alright, 333 equals to 499.5 kilonewton. So this is how much of the horizontal shear. Okay, so this is the in-plane action. So what do we want to find in the in-plane action or parallel to the wind load is we want to find out what is the NED max, what is the NED max, NED min, and also VED. This is the in-plane action. Now, for transverse action, let's see what is transverse action. Transverse action, of course, if in plane is parallel to the wind action, for transverse action it will be perpendicular. Okay, let's look at on the transverse action. Now for transverse action, actually what we want to figure out for transverse action is we want to find out what is the moment. Okay, transverse action, we want to figure out what is the moment. Okay, this is what we want to find out for transverse action. And to get this manually, okay, we can use the subframe analysis. If you remember in structure design, there's a chapter, chapter 2 or chapter 3 about frame analysis. Okay, frame analysis, we have 3 methods for frame analysis. Complete subframe, subframe at a point, apa lagi satu, simplified subframe and simplified subframe at a point. Okay, you have a complete subframe, simplified subframe, and simplified subframe at a point. And to get just the moment for the column or for the For frame, we get the column. For shear wall, we will get the moment for shear wall. Okay, and to get just the moment, we use the third method, which is a simplified subframe at a point. Okay, so we are going to adopt that technique or method, simplified subframe at a point, or one point subframe method, the name of the method. So we will use one point subframe method. Okay, and for we have like 5-story, right? You have this is 1, 2, 3, 4. Okay, 5-story. Okay, but the one that we concern here is only for level 1 here. Okay, for level 1, only for level 1. Okay, of course we are going to check for level 1 for the because the moment and also the loading for level 1 normally will be higher than the other level. Okay, so we focus on level 1. Okay, so by using one point subframe method, okay, so let's say this is your level 1. Okay, this is your level 1. So what are the height here? Level 1, level 2, level 3, level 4, and level 5. So you have here the height of the building. Okay, the height of the building, 5 times 3.5. It means that each floors is 3.5, 3.5, 3.5. But for the ground floor, you have this stump, right? 3.5 here, 3.5 here, but you have this stump, 1.5. Level 1 here is, this is level 1. This is the level that we are consider right now. Okay, so this is level 1, and the height here is 3.5 meter. The height here 3.5 plus the stump. Okay, let's do that. .5 meter, 4.5 meter. Okay, so this is the point. This is your point here. You have this loading. Okay. Now, to start one point subframe method, we start with the stiffness. Okay. Do you recall now? Stiffness equals to I over L. K equals to I over L. And since we have the same, not the same, different size of slab and also the wall, so we will have two value of stiffness. Okay. First, we are going to, this is the slab, this is wall upper. I should use different color. This is wall lower. Okay. Formula for I is BH cubed over 12, and then divided by the L. Okay, L for slab, this is L for Oops, sorry. Okay, let's do it. I have one call. It's okay. So let's calculate the K for the slab first. Okay, for the slab B and H and L. Okay, for slab B for slab, not only for the slab but for the wall also. Okay, we are going to use B equals to 1 meter. Okay, similar as the B here. Mana ke B je? As the B here. Okay, we will consider 1 meter with per 1 meter. Okay, we have 36 meter, right? But we are considering 1 meter width. Okay, so the B is 1 meter. The H is the thickness. Okay, H is equals to the thickness. Right. For slab, the thickness of the slab is 175 mm. For wall, the thickness of the wall is 250 mm. Okay, and the L refer to this. Okay, this is the L. This is the L of the slab. This is the L of the column. Okay, but okay, let's do that first. Here is 3.5, 4.5. How about this one here? Okay, let's look at the figure. Okay, here. So this is where. Okay, this is our from the elevation view, right? We have the 36 meter. Okay, but you have another grid line. This is grid line 1 and this is grid line 2, right? From grid line 1 to grid line 2 here is 6 meter. Okay, so this is the L of the slab. Okay, yang ni, right? This is the L of the slab, 6 meter. So B is 1. We are going to use a millimeter here. H is 175. H of the slab, cube over 12 and divided by 12L. Also can 6,000. You will get 0.744 times 10 power 6. No, not 10 power 6, 10 power 5 millimeter cube. Okay, and we have now slab. Let's find what is for the wall upper. K for wall upper. Okay, formula B is also 1000. The thickness of the shear wall is 250, so 250 cube divided by 12 and divided by the height of wall upper is 3.5 meter or 3,500. So this is equals to 3.720 times 10 power 5 millimeter cube. So try to get the exponent here of the same power. Okay, you might get 7.44 times 10 power 4. Okay, times 10 power 4. But to make it easier for the next step, we use the same power of exponent here. So if this is 10 power 5, so this one, if here is 10 power 5, so here should also 10 power 5. If 7.5 times 10 power 4, you might not difficult, but you have to take all times 10 power 4, all times 10 power 5 together in the calculation later. But I'll show you later on what did I mean by that statement just now. So let's calculate K. Dia jadi lagi. K wall lower. K 1000, the same thickness, divide by 12, but different height, 4,500. You will get 2.894 times 10 power 5 millimeter power 3. Okay, so next step for 1-point subframe method is, after we calculate the stiffness, is we are going to calculate the fixed end moment. Fixed end moment, FEM is equals to WL square over 12. Okay, now what is W, what is L for our case here? Firstly, W is ultimate load on slab. W here. Okay, this is your W here. So what is the ultimate load on slab? Okay, 1.35 GK plus 1.5 QK. This is from the beginning, the GK and QK of the slab. This one here, okay, the GK and the QK of the slab, not roof, floor here. Okay, 5.63, 5.63 and 4.8. Okay, so this is the GK and QK that we're going to use to calculate the W for the ultimate load on slab. So this is equals to 1.35, 5.63 the GK plus 1.5, the QK is 4.8. Then it is equals to 14.80 kilonewton per meter square. Right? Next, we can plug in this W into the formula of FEM. FEM of the slab is equals to, the W is 14.80, L, the length of the slab, 6 meter, 6 square divided by 12, we will get 44.4 kilonewton meter per meter. Next, we can calculate the moment in upper wall and moment in lower wall now. So moment in upper wall, MWU. W stands for wall, U stands for upper. So this is equals to FEM times K times the stiffness, okay, divided by the total stiffness. K wall upper divided by the total K. Okay, FEM is 44.4. 44.4 times K wall upper divided by total K. This is what I mean. K wall upper here, mana ke? This one, 3.72. K wall lower, 2.894, and K of slab is 0.744. So K for wall upper just now is 3.72 divided by the total K 3.72 for wall upper plus how much is 2.894 for wall lower plus for slab. Okay, for slab, for simplified subframe and simplified subframe at a point, method number 2 and method number 3, for slab we just take half of the K of the slab. Okay, just half of the K plus 1 over 2 times how much is 0.744. Okay, and what do I mean by the power of exponent here should be the same, 10 power 5, 10 power 5 and 10 power 5. Here you see that there is no 10 power 5, right? Because it has the same times 10 power 5 everything here. So I don't need to times the 10 power 5. This is just a ratio, so it doesn't matter. But if it is not at the same power of exponent, this is, let's say, 10 power 4, the rest of 10 power 5, you should put the 10 power 4 or 10 power 5 together in the formula here. If not, then you might get the wrong answer. Okay, wrong answer. Okay, so this will bring you a value of 23.64 kilonewton meter per meter. Okay, this is not moment. Okay, moment in upper wall. Now let's look at moment in lower wall. Moment in lower wall, WL equals to the same formula, the FEM 44.4 times K divided by the total K, but K now is K wall lower, which is 2.894. 2.894 divided by the total K. Okay, total K is 3.72 plus 2.894 plus just half K of the slab, 0.744, and this brings you 18.39 kilonewton meter per meter. Alright, so what does it mean by this 23.64 and 18.39? We are considering the level 1 just now, right? Okay, so no. Okay, this is level 1, right? So this means this is level the ground floor, this is level 2. Okay, so moment in lower wall 18.36, it is at level 1, although it is lower wall, but it's actually here. Okay, and to the lower wall. Okay, and 23.64 moment in upper wall, it is not here, not at the level 2, but still at the level 1 here, but which connected to the upper wall. Okay, so here is 23.64, here is 18.39. Okay, so this is how we get the moment for level 1 or certain level. If we want to get what is the moment for level 2, we need to do the same technique here. calculate the stiffness, calculate the FEM, depends on the W. If you get the same W, then you will get the same value. Slightly different here is the height. Okay, for level 2, you have the same height, 3.5, and this one here is also 3.5. So you will get the same K for K wall upper and K wall lower. You will get the same thing. So it might brings different here from the value of this moment in upper and lower wall for level 1. Okay, so this is it for this video. This is what we want to find. This is the objective of this video, which is to find out what is the in-plane action and also the transverse action. Once we have this in-plane action and transverse action, then we can proceed with the design of the shear wall. Okay, so I'll see you on the next step for shear wall design in part 3 video. Okay, thank you everyone and have a nice day.